Look down at these continuous, grooved treads sliding past. We step onto mechanized floors every week and call them the same name, an escalator. But strictly speaking, an escalator is a highly specific piece of machinery. It uses an articulating, step-based design, engineered strictly to climb steep vertical inclines. If you are standing on a flat, continuous surface made of interlocking pallets, you are actually on a moving walk, properly known as a travelator. Swapping these terms obscures the strict mechanical limitations of each system. It blends two entirely different architectural tools into one category. When you mislabel them, you lose sight of the specific engineering math that dictated why a facility was constructed the way it was. You will almost exclusively find true escalators deployed in shopping malls and high-rise office buildings. Travelators completely dominate the sprawling concourses of international airports and multi-level hypermarkets. That environmental split comes down to a single variable: whether the human standing on the machine is carrying cargo. An office worker carrying a briefcase or a light backpack has a completely different center of gravity than a shopper pushing a heavy metal cart loaded with groceries or dragging oversized luggage. A building's operational purpose dictates what its occupants are forced to carry, and that physical payload dictates which transit machine the architects must install. To evaluate the architectural trade-off, we have to look at the exact angles these machines are built to operate on. A standard escalator climbs at a sharp 30-degree incline. This side profile diagram illustrates exactly why that 30-degree angle is so valuable. It pushes pedestrians up to the next floor rapidly while occupying a remarkably narrow vertical footprint. For property developers building inexpensive, multi-level retail or commercial districts, conserving that horizontal floor space means preserving thousands of square feet of leasable area. A travelator cannot do this. Its flat pallets mathematically limited to a 12-degree incline. Watch the diagram when that steep line drops. The lower platform has to stretch horizontally out to the left just to reach that exact same second-floor elevation. Pushing a travelator up to a standard second-story height requires consuming massive lengths of highly valuable real estate. To move people vertically, when horizontal floor space is scarce and users are traveling light, the steep geometry of the escalator is the only financially viable option. Planners only accept the massive footprint of a travelator when mechanical friction requires it. Hypermarkets and airports demand the flat pallet design because it is the only surface capable of securely holding four-wheeled luggage carts and rolling grocery baskets. This cutaway animation reveals the hidden engineering that secures the payload. Specialized cartwheels feature distinct ridges that drop directly into the parallel grooves of the travelator's metal pallet, locking the cart completely into place. That groove lock system prevents hundreds of pounds of cargo from rolling backward down a 12-degree slope and injuring the pedestrians behind it. An escalator's articulating steps completely reject wide, multi-wheeled cargo. The treads break apart and rise, instantly pushing the wheels off balance. Hauling a heavy rolling load onto an escalator creates a severe safety bottleneck and a massive pileup hazard at the boarding and exit plates. Travelators sacrifice spatial efficiency to guarantee absolute payload stability and protect users managing heavy loads. A common assumption is that all mechanized floors are built simply to increase absolute walking speeds. In reality, travelators operate at heavily regulated, significantly slower maximum speeds compared to standard escalators. The speed is capped to prevent catastrophic pileups. If a continuous stream of locked-in shopping carts reaches the stationary exit plate too quickly, the system jams. Escalators, by contrast, focus on rapid, high-volume dispersal. They clear tight, unencumbered crowds out of bottleneck zones during peak hours as fast as mechanically possible. Escalators optimize for speed and rapid clearing, while travelators optimize for a slow, continuous momentum that simply mitigates user fatigue over long distances. When facility planners finally map out a building's transit systems, the choice between the two is a strict binary. This decision tree flowchart plots the core logistical question: is the user navigating the facility with a cart or heavy luggage? A yes immediately locks the design into the travelator branch, mandating it as the necessary infrastructure for airports and hypermarkets. A no, factoring in a tight spatial footprint, leads the architects straight to the escalator to service vertically stacked malls and offices. There is no universally superior transit machine. There is only the structurally correct machine applied to a specific logistical equation. It is time to retire the habit of calling every moving floor an escalator. The escalator is an aggressive vertical climber, a machine built to conquer tight floor plans and rapidly move dense crowds. The travelator is a low-angle logistics tool, engineered specifically to carry heavy loads safely across long, flat stretches. The next time you move effortlessly through a massive, sunlit terminal with heavy luggage, pay attention to the surface doing the work. The ease of that movement relies entirely on a deliberate, mathematical choice operating quietly right beneath your feet.